Thank you, Teresa. What's missing from the title of the talk should be clues to the origin and evolution of the solar system, and there's one word missing, and that's the word meteorites, because it's our principal source of information about the early solar system, and that's really where my talk will go today. I guess along the way I'll touch on where meteorites come from, what they're made of, and most importantly, what they can tell us. What can we learn from them about the earliest history of the solar system? Now, it might sound a rather esoteric subject to study meteorites, which is sort of like chance arrivals on the surface of the Earth, but I'm going to try and demonstrate to you that an understanding of these materials is fundamental to our understanding of the solar system and pretty much all of its component parts, and certainly the origin of the Earth. So there, I've mapped it out for us. Let's press on. But I think the first thing we need to do is to gain a kind of sense of space and time. So the first part of the talk will be me focusing on that, trying to use a broad brush and give you an idea of where our place in space is and how important that is. So in the near space environment, we have this. Now, in this diagram here, which is schematic, we've got the solar system here right at the center. Here it is here. And the orbit of Pluto, which we now know is not a planet. In fact, it belongs to a group of dark icy bodies here, this disk here illustrated, which is called the Kuiper Belt. Dark icy bodies, cometary bodies, sometimes they come into the inner solar system. And then there's this massive shell of dark icy bodies, comets, billions of them, that stretch out from the solar system to about a third of the way to the next nearest star. And that's been given the name the Oort Cloud. It's named after an astronomer, Jan Oort, and as I said, it contains billions of comets. Now, very occasionally, certainly over geological time, a nearby star might disturb bodies in the Oort Cloud and send them into like solar system crossing orbits. Now, these bodies, which turn up as comets in the solar system, may make one pass, or they may be ultimately trapped in the solar system like Halley's Comet, and so it keeps coming back into the inner solar system and going back out again. Let's focus down now into the solar system itself. So we've got poor old Pluto's missing from this, not being a planet anymore. We've got 8 planets in orbit around the central star, which we call the Sun. There are 4 inner rocky planets: Mercury, Venus, Earth with our satellite, the Moon, Mars. Then the giant gas and ice giants in the outer solar system: Jupiter, which is very important, Saturn, Uranus, and Neptune. And here we've depicted the comet coming into the solar system as well. This region between Jupiter and the orbit of Mars here is known as the Asteroid Belt. And I'll present you some evidence that will show that most of the meteorites that fall to Earth are actually bits broken from those small planet-like bodies. Now, this region of the solar system is mass poor. If you were to put all of that together, again, it would make a body only about the size of the Moon, maybe a little bit smaller than the Moon. So really, there isn't much material there at all. And there are very good reasons for that, and we'll touch on that as I go through the talk. Okay, let's take a look at some of the bodies. It looks like the Moon. It isn't. It's Mercury. Deeply cratered surface. Mercury is of course, it's closest to the Sun. It's a very dense body. It has a very thin crust and a very large core. Venus, our sister planet, it's only a little bit smaller than the Earth, but it's got a very inhospitable climate. It's got an atmosphere which is rich in sulfuric acid, or sulfurous materials, and occasionally rains sulfuric acid on Venus. The surface temperature is 300 to 400 degrees Celsius. That would melt lead. And although some Russian probes were sent to, in fact, I think they're the only ones who've been sent to Venus, of course their observational time wasn't very great because they were destroyed shortly after they landed on the surface. Then we've got Jupiter. Now, in the total story of things, Jupiter is very important indeed. It's the largest planet in the solar system. It has many moons, some of which you can actually see here. see them here. And it has played a pivotal role in the kind of form that we see the solar system in today. And I'll return to Jupiter later in the talk. This is Mars' rise over the moon, and we should remind ourselves that, in fact, we've sent, in this case to Mars, remote vehicles, not human beings yet, but we've sent equipment to Mars to study its surface and relay that information back to Earth. So we've learned a great deal about Mars, let's say, over the last 25 years or so. This is one of the probes that was put on Mars in the mid-1970s, one of two, the Viking probes, and it took a sample, retracted it, and with the equipment that it had, analyzed it, and sent that information back to Earth. But of course, since then, we've discovered that we have already in meteorite collections bits of Mars, quite a number of bits of Mars. And I won't mention it in the talk, but later on, if you want to ask me how we know it's bits of Mars, I'd be glad to answer that question. Of course, we have put people on another body in the solar system, our moon. And we've only put one scientist on the moon, and that's him, Harrison Schmitt here, who's a geologist. And he's here at this big rock called Split Rock for obvious reasons. And of course, over the entire Apollo program, 300 plus kilograms of rocks were brought back to Earth for study. So we know the moon very well indeed. And again, we've since discovered that there are also many bits of the moon that have fallen to Earth as meteorites. And this is one here. This is the first meteorite that was lunar meteorite that was discovered outside of Antarctica. And in fact, it was found here in Western Australia. So I shan't say too much more about lunar and Martian meteorites. This is Earthrise over the moon, and we have to remember that the Earth is the geologically most active planet in the solar system. And we know that it's water-rich. The surface of the planet has changed ever since it's formed. It's changed in the past, it's changing now, and it will change in the future. And basically, there's nothing we can do about that. It's a natural geological process. If we look at the surface of the moon, our natural satellite, that deeply cratered surface testifies to a period of intense bombardment by bodies in the solar system around about 3,900 million years ago. Now that event, which is called the Late Heavy Bombardment, would have affected the Earth. But of course we don't see it on the Earth's surface because of that geological activity. Basically all evidence of that has been erased from the Earth. And we can understand why. In that same 3,900 million years, seas have opened and closed, mountains have been raised and ground down to their roots again by the action of wind and water. And of course, new rock has been erupted onto the surface via volcanoes. This is not a trick photograph. Actually, it was taken by a Japanese geologist who studies volcanoes. This is a Japanese volcano, and what it shows is the volcanoes make their own climate, if you like. The hot gas and dust above a volcano can cause electrical discharge, and it can also cause inundation as well. I mean, torrential rains to occur. Right, let's look at some of that. What evidence do we get from the Earth? The oldest intact rocks that we know of are in northwest Canada here, and they are around about 4,000 million years old. Now, any older material? Yes. Right here in Western Australia, there are some sedimentary rocks which are themselves not that old, but they contain grains of the mineral zircon, which I've shown you here. And dating those, they found that they have extreme ages, 4,400 million years old. The oldest mineral grains on Earth that we know of. And what they represent is bits that were eroded from rocks of that age that were later then swept away and deposited in rocks of a younger age. So the evidence, this is what's all left of those early rocks, but we're getting very close to the age of the planet here, 4,400 million years. Beyond that, really, we have yet to find any evidence of what or basically no evidence exists of what the Earth was originally constructed from. And that's really the kind of question I would like to ask. we should look for those original ingredients and try and determine, how they were put together originally. So where do we look for that information? And this is where meteorites come in. Fragments of rock, like this one, that periodically survive passage through the atmosphere to land on the Earth's surface. And therein lies the definition of what a meteorite actually is. When it reaches the Earth's surface, we call it a meteorite. There are also fragments of metal, fragments of metal like this one. And the importance of this material is that some of it has remained virtually unaltered for the entire history of the solar system. That's 4,560 million years. So indeed, amongst these materials, we would expect to find some of those original building blocks of the planets. Okay, in a single year it takes for the Earth to orbit around the Sun, we encounter literally tens of thousands of tons of extraterrestrial material that falls to Earth. Fortunately for us, the great proportion of this is dust. About 40,000 tons of dust per year fall through the Earth's atmosphere. And we see those small grains coming into the upper atmosphere at very high speed where they're destroyed, and they give rise to that phenomena that we call meteors. Transient streaks of light that you can see on any dark, clear night. Some material, larger objects, can penetrate more deeply into the Earth's atmosphere, and then they can survive that passage, the luminous passage, to be slowed down. Even if an object has no motion relative to the Earth, if it comes in to the Earth's gravitational pull, the minimum velocity it would enter the Earth's atmosphere is about 11.2 kilometers per second, 40,000 kilometers per hour. Really very fast. So most of the material is destroyed. If it survives down here into the lower atmosphere, you see between 5 and about 30 kilometers above the Earth's surface, then it might break up and give rise to meteorite showers. And those bits will fall to Earth and we can collect them. I think the next one is a bit of video. I'm not absolutely sure. We'll find out. No, it's an example of the dust. So on the Earth's surface, those little melted particles that we saw as bright meteors do eventually float down onto the Earth's surface, and you can see this. You can see it just about. If you put it on a little glass slide, it'd be a little black speck of soot. So we call those cosmic spherules. Now, courtesy of Russian television, this is an actual meteorite fall. You can see at that high velocity, friction in the atmosphere is causing the surface of the body to melt and the air around it to become electrically charged. And that gives rise to this phenomenon known as a fireball. Now those fireballs usually go out about 10 to 30 kilometers above the Earth's surface, and any remaining material will simply fall darkly to Earth. Although the light phenomena may last for about 6 seconds, if it's falling from, let's say, 30 kilometers, the dark part of the fall would be about 6 minutes before it actually hit the Earth. So let's look at the surface characteristics of some meteorites. As I said, friction in the atmosphere causes the surface to melt. That melted material is stripped away as fast as it's formed. So it's dragging away all of the heat at the same time. And that heat is not being conducted into the interior of the object, which is great for people like me, because we want to see the unaltered interior and study it. So only in the last few seconds of luminous flight would that remaining melt solidify to form a fusion crust, and you can just see this black thing here. It's less than a millimeter thick, not very thick. So all of that means if a meteorite, let's say, came through the roof here and landed there now, would it be hot or cold? Cold, exactly. I could go and pick it up like that and carry it away. There might be some residual warmth, but essentially it would be cold. Because all of that heat had been taken away by the ablation process, but also there's another reason. That material was in the interior still at the sub-zero temperature of outer space. It's going to take it a little while to come to terms with our kind of temperatures here. So you're absolutely right, dead cold. If anybody tells you it was hot, don't believe them. I always get asked this question, are there people hit by meteorites? Well, I only know of 2 well-recorded events in history. And this lady was in a house in the state of Alabama in 1954, I think it was. And a 3 kilogram plus meteorite came through the roof, bounced off the wall, and hit her on the hip. She clearly survived this, and I'm no doubt she dined out on the experience many times after it. So, extremely rare event, and I don't know of anybody in history who was actually killed by a meteorite. Right, where do meteorites come from? This is another bit of video clip taken by an amateur, a guy with a video camera who happened to be at a football game, and I think it actually goes past the light of the stanchion in the football oval. But it's a great record. If we were able to get multiple views of that fireball from different points, and using the record, we could calculate its trajectory in the atmosphere. We just saw that. I might do it again. Let's go back. Doesn't want to go back. You could calculate its passage through the atmosphere and therefore predict where the meteorite fell. But then you could also work out the orbit of the object that gave rise to the meteorite fall. Another important piece of information. And at the end of this, you can see the trajectory in the atmosphere of this that fell at a place called Peekskill in the United States near New York, and also the fact that the meteorite hit a car and was quickly recovered. There's the car. In the last 300 years, most records, and there are only about 1,100 observed meteorite falls, most of those were quickly recovered because the meteorite hit a man-made object or fell within a few tens of meters of an observer. So that shows you that most meteorites, in fact, are actually falling either into the sea or into uninhabited parts of the Earth. And we estimate there should be around about 82 meteorite falls bigger than about 10 grams, so we're talking about walnut size, per million square kilometers per year. So to give you an idea of the number of meteorites falling per year on Australia, which is what, 9.5 million square kilometers surface area, multiply 82 by 9 and you'll get roughly the idea. An awful lot of meteorite material is falling each year. Okay, around over the last 40 years, camera networks have been established in various parts of the world. This one is in Central Europe, to make more precise observations of meteorite falls. And from these camera networks, a number of meteorites have been recovered. But the more important information, and I mentioned orbits, is the fact that the photographic record, we can use it in a special way. This is a photograph of a fireball that gave rise to a meteorite fall in Canada in the mid-1970s, 1977 to be precise. And you can see it's got special features. The camera, which is a really precise instrument, has a rotating shutter. And that rotating shutter goes at a known speed, so it chops the image up into segments, and we know the rate at which it was chopped up. So if we were going to take from this point here to an identical point there, to an identical point there, we can work out how fast this object is going relative to the Earth. That's its velocity relative to the Earth. But then we can do some really nice maths and work backwards and get the relative velocity of that object to the Sun at the Earth's distance from the Sun, and with that information we can calculate the orbit of the object that gave rise to it. I haven't put them all on there. There are some 16 now known with orbits, including 2 from Western Australia. Here's a Peekskill one. So we've got the Sun, Mercury, Venus, the Earth, Mars, and on this scale Jupiter would be way out here somewhere. So all of these bodies had highly egg-shaped orbits, elliptical orbits, that had their origin in this region between Mars and Jupiter, which I've already shown you is occupied by those small planet-like bodies, asteroids. So this is evidence, albeit circumstantial, that most meteorites we see falling to Earth are actually bits broken from those asteroids. Instead of orbital information which might indicate the body from which it actually came, of course, space agencies can go to bodies in the solar system. And this is the Japanese space agency who went to this one, Itokawa, asteroid they named Itokawa, to collect a sample of it and bring it back to Earth, which they did quite successfully. It took them about 7 years to do it. You can see here the image of the space probe. It's here, and the sun is actually behind it, shining it, and so it's casting its shadow onto the surface. It lowered a probe down to the surface, fired a bullet into Itokawa, and in a canister collected some of the dust that was disturbed. And then it brought it back to Earth. Now, we have a camera network in Western Australia, and I'll say a bit about that in a minute. And we actually recorded the re-entry of the spacecraft, which was dropped into Central Australia, and here you can see it here, caught on one of our cameras, back in June last year. So, as I said, we have our own camera network here in Western Australia. It's on the Nullarbor. We have 4 active all-sky cameras. This is one of them, quite big and sophisticated, weighs about 200 kilos. It covers an area, or the network covers an area of about 200,000 square kilometers. And we've already recovered 2 meteorites from which we've been able to calculate orbits using this camera network. This is one of the cameras operational. You can see the lid is opened. It detects when it's night. It detects whether the weather is good and not overcast, and then takes a single photograph for the whole of the night. You can see it's powered by solar cells, and it can communicate with us via satellite. So whenever it detects something, it can tell us the moment that it detects something. So on the 20th of July, 20th of July 2007, on 2 of our cameras there was this event that was, this is a light curve, so it detected the light curve, and it sent this information to us remotely. And there's a precise time, 19 hours, 13 minutes, 52 seconds, universal time. The event lasted for 6 seconds, 5.7 to 6 seconds, and there was a terminal burst, 3 terminal bursts, indicating that there were 3 fragments for us to look for. Anyway, our Czech colleagues did some magnificent work. They predicted a line, and the first day of searching, the first of the masses was found within 100 meters of that line, which is quite astonishing. This was the fireball. It wasn't a favorable circumstance. We're talking, it finished about 30 kilometers above the Earth's surface, so there we are, 6 minutes of dark flight. At that time, there were 50 km/h winds in the stratosphere, which would have deflected the object about 5 or 6 kilometers. So that makes their calculations even more astonishing. And although we recovered the meteorite, it had a very unusual orbit, the first of its kind, ever. The body that gave rise to it has an orbit that was almost enclosed within the Earth's orbit. And although it may have come from the asteroid belt originally, now it belongs, we think, to a group of asteroids which are called the Arten asteroids, which reside in the inner solar system. So that was a first for us. There's the meteorite, there was the recovered. I'm not going to talk about the types at the moment, I'm just about to get on to that. But all 3 masses were recovered, and all within 100 meters of the predicted line. Sizes, when we knocked down the Francis Street building, we had to clear out all the stuff. This is the biggest meteorite known from Australia, 12.4 tons. It was also found on the Nullarbor, and you can see that they're pretty difficult things to deal with. The guy over here is looking, going, oh my God, what's happening? Because the meteorite, as it swung off the platform, missed the corner of the building by about that much. It would have taken it clean out. Largest meteorite known, weighs about 60 plus tons, and it was found at a place called Hobart in southwest Africa. That is the largest meteorite we know of. When you get up into the hundreds of tons, or certainly into the thousands of tons, a different set of circumstances happen. Those objects are not slowed in the atmosphere, retain a huge amount of energy, and you'd end up with a crater-forming event. Now, I'm not going to talk about that today. I'm going to focus still on the solar system. Can I just have a quick sip? It's very dry in here. That's better. In around about 1972, there were only 2,000 meteorites known to science in collections worldwide, most of them in museum collections. But then a number of significant events occurred. And it's obvious the more meteorites we have, the more we're able to elucidate about the origin of the solar system. It's a bit like trying to solve a jigsaw puzzle with only 5% of the pieces and you don't have any of the edge bits either. In 1969, a party of Japanese geologists were walking along what's called blue ice in Antarctica, and they found 9 meteorites in a very short time. They took them back to Japan, and they found that amongst those 9 there were 4 different types of meteorites. Therefore, they must have come from at least 4 different falls. And then it took a little while for the penny to drop, or in this case the yen, to exactly what was actually happening. Meteorites that had fallen into the ice in the geological past had become incorporated in the ice, swept out to the margin of Antarctica, and where the ice was coming up against a barrier, like the Transantarctic Mountains, the winds were stripping the ice away and the meteorites were popping back out onto the surface. Since that time, many other countries have become involved, and there are now tens of thousands of meteorites in collections around the world. We also sort of found out, and particularly here in Western Australia, it's not difficult to spot, is it really? In Western Australia, the hot deserts of the world are also rich in accumulated meteorite falls. This is the Nullarbor region from which we've collected thousands. There are also, you can just see here my colleague, 2 meteorites sitting on the surface, not difficult to recognize because you've got pale limestone country rock and an absence of vegetation. So they really do stand out. And he's about to put them in this bag and bring them back to the Western Australia Museum for study. Same can be said for the Sahara. So here's a meteorite here. This is a German group collecting meteorites in the Sahara. So in total now, in collections, we have 50,000 or more pieces of meteorite in the world's collections. What are meteorites made of? How am I doing for time? 1, okay, not too bad. Let's get down to the business end. What are meteorites made of? And they go under the rather unscientific sounding names of stones, like this one. And I'm going to show you another view of that same slice. So it's not only made up of stony minerals, silicates, there's also a fair percentage of metallic nickel iron in here. It makes them dense objects. So they're not only unusual to look at, but when you pick them up, they're very dense and quite different from normal rocks that you'd find at the Earth's surface. This particular group are characterized by small, millimeter-sized beads of silicate material, which go under the name of chondrules. And I'm going to show you some. Chondrules is a word that derives from a Greek word, chondros, which simply means grain. Scientists are always doing that, putting complicated things, but it actually means just grain. And you can see they are spherical. This is a millimeter scale here. They range from about 0.5 millimeter up to several millimeters across. And they lend their name to this particular group, which are known as the Chondrites. Now they're a very important group because they have textures and chemistries and ages in particular, which indicate that they are amongst these very primitive materials that have remained unaltered for 4.6 billion years. Another group of stony meteorites are quite different. They lack chondrules, they lack those little grains, and they have textures like igneous rocks that we find on the Earth or on the Moon, or on Mars for that matter. So they're called achondrites, and essentially they are rocks that crystallize from molten magma very early on in the history of the solar system. Then we have the group called ions, and they're called ions mainly because they're made of essentially of metallic nickel iron. Yep, iron with some nickel in it. Now what I've done here is taken a slice, I've cut the slice, which is quite big, it's about this sort of size, polished it and treated it with acid to reveal the internal structure. Now this trellis work of different minerals formed by extremely slow cooling while it was buried in the core of a small asteroid. So it didn't form in a liquid state, it originally did, but then it cooled so slowly that these minerals dissolved. And there are other minerals here. This is the iron mineral sulfide. And in fact, these are all aligned, which indicates the small gravity that that body had as it was forming. Then there are stony ions, mixtures of metal and silicate material, in roughly equal proportions. This mineral, you would know, it's olivine, you would know it in its gem form called peridot, an iron magnesium silicate. Now, this is a very special meteorite. We know it's incredibly rare because it contains some of the oldest material that we can date in the solar system. We know it's a chondrite, it's got chondrules in it. Here's the fusion crust on the surface that I explained about earlier, but you can see the unaltered interior. And in addition to chondrules, we've got these white things here. Now, these things formed at very high temperatures at the beginning of the solar system, and they have particular chemistries, which I won't go into at the moment. But what's important is their age. 4,567 million years, plus or minus 160,000 years. That's how precise we can be with dating techniques these days. We take that as the upper age of the Earth. And we also take it as a kind of lower limit to the age of the solar system. This material was some of the earliest material to aggregate in the beginning of the solar system. Question is it the right material to put together things like the Earth? The right composition? We know they're primitive. When we analyze meteorites like that, this is an analysis of the photosphere of the sun, and this is analysis of the kind of meteorites that I just showed you. And the elements have a one-to-one correlation, except for the kind of volatile ones that tend to get messed about a little bit. So one-to-one. These are truly bits of the sun. These are truly primitive materials from the early solar system. Let's come down to Earth for a short while. And I'll try and rationalize some of this view. Although we can't see it, we know quite an awful lot about the interior of the Earth. We know it from earthquakes, we know it from rocks brought up from the great depth and by volcanoes that we can actually collect. And so about the internal structure of the Earth, we know that it's got a solid metallic inner core. We know this from the density distribution. We know that it's got a liquid, but it's still essentially metallic outer core. Then above that, we've got this massive mantle of dense rocks, iron and magnesium-rich rocks. Then at the surface, we have rocks that are rich in silicon and aluminium, the kind of continental rocks that we see. Granites and the like, and basalts that form the oceans, and which float about on this deep, dense mantle. Now, I can rationalize some of the meteorite types that I've just been talking to you about in terms of this structure. Obviously, the igneous ones, the chondrites, the igneous meteorites, come from the crusts of similarly differentiated bodies. The stony ions come from those regions between the core of a body and the mantle and crust of that body. And the ions clearly could represent bits of the cores of bodies. Now, 50 years ago or more, there was a thought that the asteroid belt represented a planet that had broken up. Well, we've known for a long time that's not true. What we see there are asteroids that have had independent histories for the entire history of the solar system, independent from each other and from any other body. But I can still use this kind of differentiated body as an analogy to give you an idea of where those meteorite types were actually coming from. Now, let's try and measure the composition of the Earth. We can do it quite simply, crudely. We know that the inner and outer core make up 32% of the weight of the Earth. And using a kind of adjusted densities, we can work out their nature. And it turns out that the inner and outer cores are less than pure iron. So there are other elements in there as well. So if you take 68% mantle and add 32% core, you'd come up with this composition. That's a composition for the whole of the Earth, iron, oxygen, silicon, and magnesium dominating, and that's the composition of the core. Dominantly iron, some nickel, and possibly a light element which could be silicon, it could also be sulfur. We don't know. The problem is that that composition, with 33 to 35% iron, is very difficult to make. So if I was going to take all those meteorite types and try and like make a cake and have the composition of the cake come out at that, I couldn't do it. There is no one single group of meteorites, nor any group in combination with another that I could produce that composition. So it's clear that the Earth itself was formed in like more than a one-stage process. And I'll finish up with that in a moment. Let's look at the chondrules themselves. I've taken a piece of rock, stuck it to a glass slide, I've ground it so thin and I'm shining light through it and I can view it down the microscope. So here's one single chondrule here. It's about 0.5 millimeter across, and it's made of these feathery crystals of that iron, magnesium, silicate, olivine, which I mentioned earlier. And it's set in a matrix of glass. Now, there's somebody who studies rocks like me, I can look at that and I would know instantly that that formed as a liquid droplet. And that liquid droplet cooled very, very quickly, so quickly that it couldn't all crystallize, and so the remaining material just chilled to glass, basically. Now, we've been studying these things for 300 years, and there's never really been a great consensus as to how they actually formed. Clearly, they are early materials in the beginning of the solar system, but exactly what generated them is still a matter of debate. But what we do know is that we can't take this sort of material and rationalize it in terms of a differentiated planetary body like the Earth or some of the asteroids. It has remained virtually unaltered for 4.6 billion years. How did it form? And there have been various kind of theories put forward. Volcanism is not viable, it's not efficient enough to generate these things throughout a large part of the solar system. Condensation gives rise to mineral grains, not liquid droplets, so we have to knock that out. Bipolar flares, well, that's interesting because the early sun did have bipolar flares, and it's possible that that melted material was generated then. Melting between collisions between bodies, possibly not efficient enough. And the one that really fits the bill is like collisions between small bodies or small primitive materials in the early solar system to produce melts that later aggregated into larger bodies. Chondrites can be made up of 80% of these little rounded chondrules. Special meteorites. This is a carbonaceous chondrite. Chondrite, you can see the chondrules, it's even got those white things which are very old, extremely old. But down here in this dark, tarry matrix here, there's something quite extraordinary. More than, 300 to 400 complex carbon compounds have been isolated from this meteorite type. The meteorite contains 28% water, easily extractable water. And I could just show you here amongst the organic material, we have amino acids. We know that amino acids are the building blocks of proteins, which are in turn the building blocks of life. Now, this doesn't represent life itself, but you have all the essential ingredients for life. Complex carbon compounds and water. And we think that these kinds of materials were added to the Earth, perhaps late on in its formation, brought water, or some of the water for our oceans, gases for the atmosphere we breathe, and some of the essential ingredients from which life might have arisen. Lo and behold, sitting next to that are these. These are so tiny that each of these is about a 40 millionth of a millimeter across. And what they are, they're diamonds. Tiny little diamonds sitting there in this tarry matrix. Some of these are much older than the age of the solar system, and we suspect that they were formed in the atmospheres of nearby stars. And as the solar system was forming, as the gas and dust cloud was collapsing, showered with these diamonds. It may even have been the trigger that set the collapse of the cloud and eventual building of the solar system in train. Now, here's the more we look, the more we find. And amongst these great numbers of meteorites that we're actually recovering these days and putting into collections, we find odd things like this one. It's an igneous rock, okay? It's an achondrite. But it's got an age 4,566 million years. You've got an age that is almost close to the most primitive materials that I've been showing you, which is a bit of a real strange thing. But what it means is that we think that there were a generation of differentiated planetary bodies that formed very, very early on in the solar system, and bodies like the Earth and probably the inner rocky planets also were formed by collisions between these already differentiated bodies. Hence the strange chemistry of the Earth, hence the fact that we can't match it to some of the more primitive materials. Now the parent materials of this, well, we have yet to see them, if indeed they still exist. So finally, this is my last slide. Let me try and pull that all together for you. So from that study of meteorites, we can deduce a number of major things. Around about 4.6 billion years ago, there was fragmentation and collapse of an interstellar gas cloud, which we call the solar nebula. Material condensed from that very rapidly, stuff starting to hit each other and stick together, build into smaller bodies that later snowballed into larger bodies, and then eventually swept up into the planet-sized bodies. The early sun had a vigorous phase, and what it did, it purged the inner solar system of volatile elements, sent it towards the outer solar system during its really vigorous stage. Now, there was a body out there called Jupiter, which we call Jupiter, that was gathering a lot of this material. And by the time that it reached about 10 times the mass of the Earth, 10 times the size of the Earth, it started to dominate that part of the solar system completely. It prevented any large body from forming in its near vicinity. So hence we've got this rubble left over after the formation of the planets, the asteroids. It ejected a lot of material from the solar system, and then eventually it sent a lot of material back into the inner solar system, where we saw evidence of that through that late heavy bombardment, the cratered surface of the moon. And presumably the Earth gained material from that as well. Now of this material, of this rubble left over after the building phase, some of them remain unaltered, from which we think we're getting the chondritic material. Some of them did differentiate. They melted and separated into crusts and cores, from which we see those igneous meteorites and the iron meteorites. Through collisions and Jupiter's gravity, many of these were either destroyed or bits knocked off them, and they were sent into the inner solar system, where we see them falling today as meteorites. Thank you very much.